Hello everyone, and welcome to my playlist on analysis of algorithm. In this first video I will focus on recurrence relation and how to reduce them to a simpler sum. This method is described in concrete mathematics from Knuth, especially chapter 2, page 27. The recurrence relation is of the form, an Tn equal Bn Tn minus 1 plus Cn. That's usually the form you find in most of the analysis of algorithm. Tn is the recurrence relation and A, B, and C are the coefficients. So we try to use the summation factor method, which is almost very mechanical and very easy to use. I'll take the example page 28, which is the Quicksort recurrence relation. Let me show it to you. Just a moment. Here we are. So you can see the search for the pivot. This is the cost and the cost of the two sub-partition sorting. So in very classical, nothing special here. The book gives us the first few iterations. So we have C1 equal 2, C2 equal 5, C3 equal 26 over 3. So of course I recommend that you first read the chapter and then come back to the video to see the example in more detail. So the first thing we want to do here is to get rid of the division. So to do this, we'll multiply by n the recurrence relation. So we'll have n Cn equal n squared plus n plus 2 over the sum Ck with, of course, n greater than 0. The second step will be to get rid of the sum, and to do this we'll use a two-step method. So first we take the same equation with n minus 1, Cn minus 1 equal n minus 1 square plus n minus 1 plus 2 over n minus 2 Ck. And then we'll subtract the second one from the first one, and that will allow us to get rid of the sum, because when you have C1 plus C2 plus C3 plus C4 minus C1 plus C2 plus C3, only C4 is left, of course. So that's what we want to do here. So let's employ this method and do it. Okay, sorry. So n Cn minus n minus 1 Cn minus 1 equal n squared minus n minus 1 square plus n minus 1 plus 2. So this is n minus 1 equal 0, Ck minus 2 and minus 2 Ck. So we're left with n squared minus, let me expand this to n squared plus 2n minus 1 plus n minus n minus 1 equal 1 plus these two sums almost cancel, and we are left with 2Cn minus 1. the two squares cancel, minus 1 plus 1 cancel, and we are left with 2n plus 2cn minus 1. Okay. So let's go down further, and we take this term to put it on the right side. So we are left with n cn equal 2n plus n minus 1 cn minus 1 plus cn minus 1 plus cn minus 1. I do expand these two terms here. So you can easily see that this gives us n plus 1 cn minus 1. So we have come to the result of the book in page 28, end of the page 28. So we can now apply the method of the summation factor with an equal to n, bn equal to n plus 1, and cn equal to 2n. In fact, the form should be n cn n plus 1 cn minus 1 plus 2n. That'd be clear. A, B, and C. So now we are ready to apply the summation factor as described in the book. So I will refer to chapter 2 of the book Concrete Mathematics to understand why it does work. Here we just apply the formula. So we're looking for S of n, which is equal to a n minus 1 times a n minus 2 up to a1 over b of n times b of n minus 1 times up to b2. Remember that a of n equal n and b of n equal n plus 1. In our case, so this reduced to n minus 1 times n minus 2 times up to 1 over n plus 1 times n minus 1 up to 3. We can easily show that in general this reduced to 2 over n plus 1 times n. Let's try to show it with a few cases. For example, when we have 3, so we have 3, 2, 1 over 5, 4, 3. So you can see that the 3 cancel, and we are left with 2 over 5 and 4. The same with 4. Over 6 times 5 times 4 times 3. So 4 and 3 cancel, 4 and 3 cancel, and we are left with 2 over n plus 1 times n, and so on. Now the book applied the summation factor to the formula Sn to Cn, and reached the conclusion that Cn equal 2n plus 1 summation with n, 1 k plus 1 with C0 equals 0, and that's it. So I think it goes pretty fast, and I'll go into deeper details to reach the same conclusion. So let's try. Okay. So the method is described using equation 210 of the chapter 2. I'll show you this equation to you. Here it is. It's coming, sorry. Okay. So you need to apply this formula, this equation, to the summation factor. So you can see the summation factor is applied here as Sn and Sk. So T0, in our case C0 is 0, so this term is cancelled, and so we are left with, in fact, Cn. So the confusion between Tn and Cn is a bit also annoying in the book. So Cn 1 S of n an of the sum Sk Ck, k equal 1. That's what we want to do. So we need to replace the Sn and the Sk with the proper summation factor. So to make sure we are on track, we'll apply this formula to the first few iterations. We already know the results, and so we'll see that they check. So let's take C1. C1 is 1 over S1 A1 times S1 C1. So I put here S1 is 1, S2 is 1 over 3, and S3 is 1 over 6. So here we have times 1 times 1 times 1 times 2 give us 2. So far so good. Let's try C2. C2 is, so this time we expand the sum, so we have S1 C1 over S2 A2 plus S2 C2 over S2 A2. Does give us, for the first, 1 times 2 over 1/3 times 2 plus 4 over 2, which gives us 1/3, the 2 cancel, plus 4 over 2 is 2, which is equal to 1 over 1/3 is 3 plus 2 equal 5. So far so good. Let's try for 3, C3. So this is S1 C1 over S3 A3 plus S2 C2 over S3 A3 plus S3 C3 over C3 A3. So let's expand this. S1 C1 is 2 plus 1 over 6 times 3. S2 C2 is 1/3 S2 times C2 is 4 over 1/6 times 3 plus S3 cancel, so we have C3, which is 6 over 3. Thus we have here 4 plus 8 over 3 plus 2. 8 over 3 plus 6 equal 26 over 3. So far so good. So let's go back to our formula over here and try to simplify this formula. So let me erase these. Okay. So Sn, we know what it is, so we can go into more details. Sn is 2 over n plus 1 times n times n. This is an times, so sum of k equal 1 of n. Again, sk, we know what it is the same as Sn, so it's 2 over k plus 1 times k times ck is, we saw that it's 2n, so it's 2k over 1, just to be consistent. So this 2n over n plus 1 can be replaced by n plus 1 over 2 time summation k equal 1 of 4k over k plus 1 times k. So now without loss of generality, we can make n equal to 1 and get rid of the sum for the moment. So we are only left with n plus 1 times 4k over 2 times k plus 1 times k. So we can see that the k cancel and the 4 become a 2. So we have 2n plus 1 times 1 over k plus 1. Now we can reintroduce the sum, 2n plus 1 times sum k equal 1 of 1 over k plus 1. And that's the formula we have in the book. Now let's focus on the summation. We'll notice it's very close to the harmonic numbers. So let's see the definition of harmonic numbers. So let me erase all these. Harmonic numbers are defined this way: 1 over k. So it's 1 over 1 plus 1 over 2 plus 1 over 3 and so on. So notice that in our sum, I'll put it back here, time 1 over k plus 1, we are very close to harmonic numbers, to the definition of harmonic numbers, but we are shifted right once. So instead of starting here over n over 1, we start here and we end n over n plus 1. So we can say that our definition here is the same as the harmonic number 1 over k minus the first element plus the last element of the series, n plus 1. And we can reduce this to the harmonic number n minus this definition here, these two terms, here, which are equal to n over n plus 1. So if we plug this knowledge back to our equation here, we get, and that will the last term. Let me go down a little bit. So we get Cn equal to 2n plus 1 times the harmonic number h of n minus n over n plus 1 times 2n plus 1, which is the summation factor here, the factorization that we shouldn't forget. And finally, the last term, final equation, gives us 2n plus 1 times h of n minus 2n. Thank you for watching.